Welcome back to ECE 320A. We're in Unit 2, Lecture 5 or Video 5, and homework number 2 will be due at the end of Unit 2. And just as a reminder, Exam 1 is coming up at the end of Unit 2, and you can find review material for that on D2L in the module entitled Exam Number 1 Review Material. What we want to do today is actually work through an example of analyzing a network of loads, and we've talked about that before, but here is a particular illustration that it bears that out that we've been talking about. We have 3 different loads. I've labeled them load 1, load 2, and load 3. And with each load, you're given maybe different kinds of information as far as the types of power associated with those loads. Load 1, you have no reactive power and you have purely real power. Load 2, you have a combination of real power of 200 watts and reactive power of 700. It's inductive, so the Q would be positive in load 2. And in load 3, you have a capacitive load with a reactive power of 1500 VARs and a real power of 300 watts. And what we want to do now is examine or analyze this multi-load network, and in particular, to give us something to work on, let's now find the current that's being supplied to those particular loads when the voltage across that combination, and you have a couple of loads in parallel and then you have a series load feeding those 2 parallel loads, but at the source side of this network you have an RMS voltage of 100 volts and it's at an angle of 0 degrees. So really our voltage is the reference phasor in this particular case. And let's see if we can find now this RMS current. And before we do that, maybe, well, the idea really is we want to find what all of these loads look like in aggregate so that we can then find the current that's required at the voltage of 100 volts at 0 degrees to support those 3 loads. That's the idea. Well, in order to find what I've now highlighted in yellow, I need to now try to find the total complex power in this system, and I can do that from before by adding up the component parts of the individual load powers. The real parts or the average power, I can add those up algebraically. I can add up the reactive powers algebraically. So let's do that. And here's what we were given in terms of information, and we can actually keep track of that in a tabular form. We were told the information in component parts. We were given in rectangular form the real and reactive pieces of those powers for load 1, load 2, and load 3. And you can see that I've put the appropriate sign on those reactive pieces. The inductive load in the reactive power is positive 700 for load 2, and in the load 3 it's negative because it was capacitive. Now we can find each of the load's complex powers, and let me write those in. Let me say that those now are in red. S sub 1 is simply a 100. S sub 2 is a complex quantity, 200 plus J 700, and load 3 is now 300 minus J 1500. And as I said before, we can actually add these up component-wise. We can add up 100, 200, which is 300, plus another 300, or a total in aggregate of 600 watts of real power reactive, we need to keep track algebraically of those, and we end up now with minus 800 for the reactive power in total. And so we can either sum horizontally and keep track of the real and reactive pieces, which is probably easier than trying to add up the real and reactive parts of the rows above, but we can see that we have 600 minus J 800 for the total complex power in this system. We could also, just for illustration purposes, find the apparent power in each of those loads. The first one's easy. It's just the magnitude of 100, which is 100. The other two, we have to actually find the hypotenuse of this right triangle. Load 2 has a horizontal leg of this triangle of 200 and a vertical leg of 700, and the hypotenuse is now the sum of the squares and the square root of the sum of the squares, giving us 727. The sum of the squares of the load 3, we have 300 over or horizontal and 1500 down. We end up with it being 1,530 in terms of the apparent power or the length of the hypotenuse. And I think from that particular column on the far right and this total, you can now see that if we computed the apparent power of the total of the three loads, we would now be looking at the magnitude or the hypotenuse of a triangle that has one side 600, another side 800, and I think it's clear that that now ends up with our apparent power of the total being 1,000 volt amperes. And that's obviously not equal to 100 plus the apparent power of load 2 plus the apparent power of load 3, which ends up being 2,357. So those, I hope, help illustrate the fact that you can't add directly the apparent powers to end up giving you the apparent power of the total. That's what the red and blue there are trying to indicate. So now we're looking for I sub s, reminding ourselves of what we have. We've now found the total complex power associated with the combination of those three, and it didn't matter how they were interconnected. What we want to do now is find this current that's required to support that particular combination of loads. And what we're really doing, if I illustrate this maybe with a picture, we now have all of those loads in aggregate looking like 600 minus J 800 volt amperes. And we know supplying that is a voltage phasor in RMS of 100 at an angle of 0, and we're now wanting to find what is this current of the source that will actually produce that total complex power. And I hope now that you've worked with this enough that you can remember that now your formula for the complex power of a system, and in this case, that red blob is really just a system, and we know its voltage, and we're trying to find its current, but we know that the complex power is this product of voltage times the complex conjugate of the current. And now that we know that, we know the left-hand side, we know the total complex power, we know half of the right-hand side, we know the voltage phasor, we can actually now solve for the current phasor. And remember, we're using RMS for voltage and current in this particular case. Well, we're not solving for I sub s directly. We're solving for the complex conjugate of I sub s, but that's okay because once we have that value, it's not hard to find the actual current. But let's now solve for the complex conjugate of the source current. That's now the total complex power divided by the voltage phasor. In our case, that's now 600 minus J800 divided by 100 at an angle of 0. And if we wanted, the 100 could pretty easily go into each of those, and the angle being 0 downstairs doesn't make that very difficult. And so we really have 6 minus J8 in terms of a value. Or we could say, let's now convert that numerator, the total complex power, into a polar form representation so that we now have 600 this way. We have 800 for the reactive power down, and we now are looking for the length of that hypotenuse and this angle theta. And if we do that, I think it's clear that the amplitude or the value of that hypotenuse is 1,000 with a 6/8 or 3/4/5 triangle effectively. And the angle now, you can see that it's a negative angle, and it's the inverse tangent of minus 800 over 600, since we are going minus 800 down, and that ends up being an angle of minus 53.1. So this angle is minus 53.1 degrees. That's the angle of the current. I'm sorry, that's the angle of the complex power, which, because the angle of the voltage is 0, ends up being the angle of the conjugate of our current. But I hope that now from this you can see that the complex conjugate of our current is 10 at an angle of minus 53 degrees, subtracting 0 from minus 53. That's in amps. We can now find the actual current in our system. It's the conjugate of minus 53, which we can find by simply changing the sign of minus 53 to give us plus 53. That's now an RMS magnitude of 10 at an angle of 53 degrees, and that's the amps. And remember what our voltage was. Our voltage was 100 at 0 degrees. So now that we have the current and the voltage, we can actually say a little bit more about the net effect of those three loads in combination, or in particular, what kind of a load does this present in aggregate to our source? What's the type of load that our source is seeing? And now you can go back to something that you probably need to remember until you retire, which is Eli the Iceman. And the reason why you want to remember that is because it now tells you how the currents and the voltages are connected or related to one another for the inductive load and for a capacitive load. For the inductor, Eli says V is equal to L di dt, but just ELI tells us where the current is relative to the voltage, and the current in this case is actually lagging or lags the voltage. It's after the voltage. And in the capacitor's current I is equal to C dV dt. And in this case, the current is coming before the voltage, or the current actually leads voltage in the capacitor. So with that Eli and ice as an aid, can we use that to determine what kind of a load we have in this situation in aggregate with a voltage that has an angle of 0 and a current that has an angle of 53? So now we can look at the power factor of our total load, and that's now the cosine of theta total, or that's now the cosine of the angular difference between the voltage and the current. Remember that angle theta is related to really an impedance angle. And in this case, we can say then that the total impedance is, by the generalization of Ohm's law, is V over I. In our case, we had the voltage magnitude at the angle of the voltage, and we have our current magnitude at the angle of our current, or we now have the magnitude of our impedance where our total angle now is theta sub V minus theta sub I. And if we go back to what we've already found, we had theta sub V is 0 minus a theta sub I, and theta sub I in this case is 53. So we actually have an angle of theta equal to 0 minus 53, or now we can say that the power factor total is now cosine of minus 53.1 degrees, which is 0.6, and the fact that this angle is negative doesn't give us any indication by taking the cosine. So because of that, we have to keep track of that minus sign by saying that the angle is actually, or I'm sorry, the power factor is leading in this particular case, because now if you look at the current, it's at 53 degrees, which is a larger angle than the voltage angle of 0. And when we have a current that leads the voltage, then we have a capacitive circuit. Our circuit is a capacitive overall looking network, and we have a power factor of 0.6. So now we found one piece, actually more pieces. We found the actual magnitude, we found the power factor, we found the current, we found the power factor. What if we wanted to find something a little bit more? We've now found the current supplying that combination of aggregate loads, but what if we wanted to find the current of one of those loads on the right? And in particular, maybe the far right load, we might be interested in finding that. So how would we find, let's ask another question, how would one find the RMS value of I sub 3? And let me go ahead and draw the picture again to remind us. Here's load 1. Here's load 2. And here's load 3. And what I'm really after, and we were given this voltage. We just determined this current, which in fact is this current, because it's in series. Load 1 is in series. But now what I'm asking is, what's this current? And we have a current division problem, really, but we don't have necessarily that information available to us. We don't have this in the form of impedances. So now we want to know what actually happens relative to I sub 3 and load number 3. And what we can do is we can start to say, well, we know this current And what else would we need to know? Well, if we knew that combination of loads, then we know that complex power of those two, and we know the current, then we could actually try to find, or we could compute the load voltage across those two loads that are in parallel. And it's not hard to find that complex power of loads 2 and 3. We simply have to add those two up algebraically. The process then that we're going to use is we're going to find first the complex power that I'll call S sub 2, 3, which is just the combination of the complex power of load 2 with the complex power of load 3, which is now 200 plus J 700. Is that what we had to begin with? 200 plus J 700, and then we have 300 minus J 1500 for load 3. Or we now have the complex power combination of loads 2 and 3 is now 500 minus J 800 volt amperes. Now that we have that, we can use our complex power formula. Now we can actually find the voltage across those two parallel loads. And now we know that the complex power of those two loads will equal the voltage times the current. And the current supplying those is the original source current, I sub S, and we need to use VI star for complex power. Now we can use that relationship for complex power to solve for the unknown that's not yet available, which is the voltage dropped across those two parallel loads. And that's now just a math problem with some complex numbers. We have the complex power S sub 2, 3, and we're going to divide into that the conjugate of our current that's supplying those three loads, which it's going through load 1, it's supplying those two. And we just calculated S23, which was 500 minus J 800. We can divide that by the conjugate of the current, 10 at an angle of minus 53. And we now have then V sub L is 943 at an angle of minus 58 degrees over 10 at an angle of minus 53 degrees, or we now have 94.3 at an angle of minus 5 degrees. And that's our voltage dropped. And what did we have before? We had 100 over here. And it makes sense. We've dropped some voltage across load 1 before we get to the load, or the two loads in parallel, which then have a voltage drop of V sub L, which is now 94.3 at an angle of minus 5 degrees. Now do you see what we can do? Now that we have this voltage, we know S sub 3, we can use again complex power formula to find I sub 3. And that's step 3 then of this process. We can now find I sub 3 from S sub 3 is equal to the load voltage, V sub L, the voltage dropped across loads 2 and 3, times the complex conjugate of I sub 3. And now we solve for the unknown in that formula. I sub 3 conjugate is now S sub 3 over V sub L. S sub 3 was 300 minus J 1500 over 94.3 at an angle of minus 5 degrees. or converting 300 minus J 1500 to polar form, we have 1529, and you should think that that's a large negative angle, and it is. It's minus 78.69 degrees, all divided by something a little bit less than 100, 94.3 at an angle of minus 5. Doing the math, we now take 94.3 into 1529, and we end up with 16.22 at an angle of minus 73.69 degrees. So that now we can say that the current through the third load is now 16.22 at an angle of 73.69 degrees by conjugating that, and that's now an RMS value, and we have 16 amps supplying load number 3. And if you're remembering what we just calculated, what was the source current, I sub S? Wait a minute, I sub S was 10. It was 10, and now we have found that this current, I sub 3, is bigger than 10. What's going on? What in the world do we now have going on? Did we make a mistake? Is that even possible? So let me just write that down. What do we have? Note, what we've just computed and found is the magnitude of load 3's current, I sub 3, which was 16.22, is bigger than the current that's being supplied by the source, which was 10. What's going on? Well, in fact, this is what we're going to have in a little bit when we start talking about power factor correction. But remember what the relationship was between loads 2 and 3. Load 3 was capacitive, load 2 was inductive. Those two are not in the same sort of direction in terms of reactive power. They're sort of playing off of one another. And in fact, the current at the loads 2 and 3 is really sort of being passed back and forth at the load end, and so the source doesn't need to be delivering quite the amplitude of current that's actually required at the load side, or the load side being loads 2 and 3, than what's required overall. So in this case, load number 2 and load number 3, since one was inductive and one was capacitive, they are actually passing currents back and forth without having to worry about going all the way back and requesting more current from the source. And that's what we need to start becoming a little bit more comfortable with when we start thinking about power factor correction. So this example actually leads us into a subsequent topic, which we may not get to immediately, but we will get to it before we complete Unit 2, and that's on power factor correction, which is introducing maybe a capacitive type load to try to make our power factor look a little bit better or get closer to 1 than what it is when we don't have that capacitive load introduced. And we'll pick up with that concept in a subsequent lecture.